Going live now. All right, we're live. Hi, everybody. Welcome back to the Renaissance Builder live stream tonight. We are continuing to work on the driver, the variable, it's not a variable speed driver, but the variable, it's a phase angle driver. We're working on this component. We got this. This is successful. We're happy with it. So we're going to work on the next step of that, which is designing the rest of the driver components. Oh, and I say that, and I went and forgot the pieces I left on the bench. The pieces that I need to do this, I went and left on the bench. So, pardon me whilst I add some. First, I need to pull up the live stream because, well, I got the comments right here. I don't need to have that right in front of me, so I got the comments right here. Good enough. Let me do some advertising. Because, we got to do that every time. We have to advertise every time. Be nice if I had a person for this. Vertical live streaming is here. Don't care. We are live. Share. Copy link. And we are live. Hi, everybody. Next. Share. Okay. A little bit of advertising for that. All right, now let's get into the meat and potatoes of this. All right, so the next step in our machine. So maybe I'll go over what it is we're building. Let me run over here a second and grab a couple pieces. I'll be right back because it's just right here. Ta-da! All right. Let me put the mic back on. Now, to go over again what it is we are working on, I have in my hand it's actually the heater element of a coffee maker, a commercial bun coffee maker. So this is the heater element of said coffee maker. It's really nothing fancy. It's just an electric strip heater underneath here. And we just got to drive it. Normally, you would just put 110 volts straight to that, and this would just get as hot as it gets. Not sure how hot that is specifically, but I know it's hot enough to make your coffee hot. Whole lot of variables. So what we're doing with this is we are making a driver circuit that will allow us to plug 110 volts in and then turn a dial to choose a set point of a certain temperature, telling the controller that we're going to be putting in here, so telling a microcontroller to variably drive the AC current into this thing in such a way to meet that set point. So that means that we need to have a driver to drive the AC current, and that's different than DC. DC would be very easy. We'd just put a MOSFET in there, pulse width modulation, no big deal. AC, it's a bit different. You actually want zero cross detection, and then there's like a whole counter. It's a little process. So we're going to need a temperature sensor. It's going to go right in here. That'll be a bit custom. So we're going to put a temperature sensor in here, a microcontroller in here. We're going to have a screen readout so that we know what the temperature is and what we're looking for, like what our set point is and what the temperature is and how much wattage it's actually using. And then a dial. And that'll do it. That is what we're working on. Now, I have, what the previous live streams were doing is we were developing this here zero cross detection circuit. This isn't a normal zero cross detection circuit. It is actually an adjustable Again, in those live streams, we went over why we wanted adjustable, but that's this. So we have that part. Now, we need the actual driver part. That's the solid state switch that the microcontroller is going to use to actually vary the power to the heater. So we're going to go back to our Fulstad Circuit.js1 program, and we are going to start designing this circuit. Let me pull this over. I can close this down, magnify that up, and this is the generic thing that they send you. Right, so I want a new blank circuit. Okay, now, before I get into this, I should probably lay down a couple things. I can actually draw this out real quick. If we were doing a standard DC circuit, then the components we would be using is something like a MOSFET, right? Oh, Jesus. Nope, that's just weird. So, a MOSFET. And what a MOSFET does is we come in one side, we send power into here, and we get power out here, and this is the gate. So this, you can think of a oh, bloody, sorry about that. I need to change the, I really need to change the shortcuts on this stupid Streamlabs. Frankly, I need to dump Streamlabs as a whole, but that's a different subject. So this is a MOSFET. It's a solid state switch is what it is. MOSFETs are unique in that this little joint, this little junction right here, MOSFET, it's a metal oxide. Oh, I should know this. No, I don't remember. Basically, the gate of a MOSFET is a little mini capacitor. And the reason that's fun is because we can use control level voltages to turn it on. But that's DC. MOSFETs only work when the current is going in one direction. Now I have designed, in fact, circuit. Oh no. That is going to get very, very annoying. I need to, can I change that on the fly? Because I need to change that. I definitely need to change that. Hotkeys. Let's see if it will let me go back to all. Click to rebind. Start streaming. Transition all studio mode. Disable toggle. Intermission. What this is it keeps going to, what does it keep going to? Builder bench? Oh, this is not good. I hate Streamlabs so much. Alright, here it is. Alright, backspace. Now let's see if it works. Done. Let's see if I fixed it. Did I fix it? Yay, I fixed it! Urgh. I hate Streamlabs. Anyways, okay, where were we? Alright. The MOSFET. MOSFET, let's see. Can I draw an arrow? I can. MOSFETs only go in one direction. Right? The body diode and the a MOSFET is similar to an SCR, which is silicon control rectifier, which is basically a diode that you can turn on and off. In fact, a lot of circuits are built around that idea, which is fine. That's how they work. What we want to do, AC, alternating current, is kind of how it sounds. AC goes back and forth. It goes in both directions. So what we want, the component that we actually want, is called a triac. Now I'm going to plant this sucker right over here. Oh, I want it the other way around. This is called a triac. Now, if you'll notice, the whole diagram of a triac, it looks very similar to a diode. So if I draw a diode, see how that diode looks? And then if I went the other direction, haha, check that out. It looks like a triac. That's because it's very, very similar. Let me get rid of these. So a triac is essentially an SCR, which is silicone controlled rectifier, which is kind of like a switching diode. It's a check valve that we can turn on, like we can manually open it. And what they do is they put them in both directions so that when you turn it on, turn them on, no matter which direction the current's going, it can get through, right? So when you're running alternating current, you turn it on, no matter which direction the current's going, it'll get through the triac. That is what that's all about. All right. Now, that's why we use that specific circuit. Now, I have a few different triacs that I can use in this machine. I don't know 100% yet, and we're going to have to go to the lab. We're going to have to go to the bench on probably the next live stream. We're going to go to the bench, and we're going to physically test using a voltage drop to check the resistance of this heater. And you might ask, why not just measure the resistance? Well, resistance can change over temperature. With this, it's very linear. But what we want to do is we want to actually put a voltage to it and then check the current. Once we know the current and the voltage, then we'll know the exact resistance of the element. And we can actually plot the resistance over the temperature band. But we're going to use Ohm's law to calculate the resistance on that. It's a more accurate way of checking the actual resistance. So, what the circuit we're going to design today is centered around this here triac. The second part of the circuit that we need is an optocoupler. Now, an optocoupler, and I'll show you one here, allows us active building blocks. Here we go. Now, here's the thing. This optocoupler drawing is not correct for what we are going to use. But this little diagram does demonstrate what an optocoupler does. The name kind of gives it away. It's an optical coupler. And what that allows us to do is to use a microcontroller, like a little mini computer, to turn on a high voltage device without affecting the microcontroller. Since there's a physical barrier, it's a light and a light reactive element, it can't go the other direction. So the optocoupler allows us to be able to manipulate the high voltage without the high voltage affecting our microcontroller. That's what an optocoupler does. The reason this one isn't exactly right, and that's part of the limitations of this simulator, but the reason this one isn't exactly right is because this one is drawn as a transistor. So it's a transistor-based optocoupler, which is fine, but in our situation, we don't want a transistor because a transistor only works in one direction. Again, you can see this little body arrow here. A transistor only works when the current is going in the one direction. But AC goes in both directions. So since we're controlling an AC device, we need to be able to control it with an AC optocoupler. So what I'm going to do is I'm actually going to draw so there's both versions. The 4N25 optocoupler is what we just saw on screen. It's a transistor-based optocoupler. The other version is the MOC optocoupler. The MOC is actually a triac that reacts to the LED. So it's an optocoupler, triac-based optocoupler. So we can use a triac, a little mini triac, to turn on our bigger triac. So what I'm actually going to do is I'm going to cheat. Since I want the triac, I am going to active components. I'm going to draw a little mini triac. And I'm going to put it in a box. Oop, that's not what I wanted. I want it right here. All right. And I'm going to feed this triac in order to simulate the way that we're going to control this circuit with a microcontroller. So this simulator doesn't let me actually program a microcontroller in that. Some simulators actually allow you to do that. This one does not. But in order to essentially simulate what I'm looking for, I am going to... let me give it a square wave source right here. And I'm going to see if I can simulate what we're going to feed this with this. It's going to take a little experimenting, but that's why we're here. Jesus Christ, the viewers. All right, whatever. So what I'm going to do, I'll shorten that up a little bit. All right, and just for the sake of knowing that this is an optocoupler, I'm going to go ahead and put a box around it. And give it an LED. Outputs, LED. Ah! There we go. There's our optocoupler. Alright. Do I want to do it that way? I mean, that's kind of how they draw it, but it doesn't need to be. Okay. Let's draw this one over here. Alright. And then I'm going to draw this. Now I can erase that. And I need to put a resistor in here. And the diagrams, the examples that I've seen... Huh, that is off the screen. Why is that not fit to screen? Transform. Stretch to screen. Fit to screen. Maybe I need to go here. Screen capture. Fit. Transform. Fit to screen. Oh, nope, that was the wrong one. I'm doing such a great job. It's alright, nobody's watching anyways. Display capture. Transform. Fit to screen. That still doesn't... Why does that... Oh, that's weird. Okay, that's odd. Looks like I need to... Looks like I just need to pull this component back in a little bit. There we go. That doesn't matter. Alright. Now, I should be able to... Okay, I need the load. So here, I'm going to have a power source. And then here... Alright, I'm going to have the power source over here. Let's go ahead and draw out there, disturbing notifications, and wire there. I like to draw these things out just so that everything ends up square, because I'm kind of OCD that way. Now I'm going to draw inputs. I'm going to draw AC voltage source. Oh, that's one terminal. I need two terminals. AC voltage source. Ta-da! And I'm going to set this to our voltage source, 171.6 and 60 hertz. Okay. Now, this one, why does that keep making me have to do that? This, I want my load. Now, outputs, it gives me an LED and a lamp. But realistically, it's just going to be a resistance. So, I really should just add a resistor to that. And the resistor is going to be pretty low. We're going to call it 10 ohms. In fact, I could probably measure it. Just the dry resistance. And I want to take this down, bring it over, and back to there. Oh wait, no, I'm an idiot. That is not correct. I want to take this and I want to bring it to the gate of this triac. Okay. Now, here's the tricky part to this circuit. At this point, this resistor right here is our load. This is, honestly, it's a really basic circuit, but this is our load. This is our switch. So this triac right here is our main switch. And this is what would be called the pilot duty switch. So this little mini switch is going to use the voltage from our controller to turn on the bigger switch, which will control the load. I believe I need to edit this source. Okay. This is where it gets a little bit tricky and I need to do some math. In order for this to imitate, assuming this input is actually going to trigger that triac, in order for this to imitate what we need to do, it needs to pulse width. In fact, let's see if I have a pulse width. I don't know if I can control that pulse width. Phase offset, duty, yeah, duty cycle. Okay. So in order for, all right, this max, this voltage, I don't know what this voltage is going to be, but let's just say, yeah, let's just say 5 volts for now. All right, this is going to start on. I kind of need it to start off. And what we want it to do is we want it to have a pulse. So pulse width modulation is, you think of one pulse as, let's say our one pulse is 8.25 milliseconds long. 50% duty cycle means that that pulse is on for 4.175 milliseconds and then off for 4.175 milliseconds. That's a 50% duty cycle. So the pulse is on half of the time of the pulse. And since AC does a sinusoidal pattern, 60 hertz is it swings an entire positive to negative and back again. It does that 60 times a second. Well, we want to pulse every loop. So we want to pulse once for the top and pulse once for the bottom part of that. So we want to double. We want our pulses to essentially double the 60 hertz. So we're going to set it to 120 hertz frequency, which should give us a pulse width of the one loop or half of the sinusoidal phase. Right. Now, I kind of wish it would offset in degrees. Let's give it 120 degrees. And that might offset, and that might give us the backside of the pulse. Because I think it starts on and then goes off. I think that's what this is doing. Does it let me invert? DC offset. No, not really. Alright. Let's see what happens. Run. It's technical difficulties. Why? Why are we not running? It's not. Wire loop detected. Alright, maybe I need to get rid of some of this. Maybe I need to get rid of some of that noise. Oh, there we go. Okay, now let's take the oscilloscope and see what's actually happening. I don't see any current moving, so it would seem that... Let's see, that... Supposedly... View a new scope. 1.72 millivolts. It is not dropping anything. We have our voltage set right? Yep, Okay, maybe... I'm going to take this to... I'm going to take out the phase offset. And I'm going to set this to 100% duty cycle. Okay, it's not... Let me up the voltage. Max voltage, let's give it 100 volts. No? Not okay. This is... Okay, what if I take this out and bypass that? Still nothing. This... Interesting. So the switch isn't actually turning on. Why not? Do I need to change this? Trigger current, 10, holding current, resistance and ohms. Well, this is about to be a very short live stream because now we're not working. Think. We have... Do I need to be on the... Alright, let me try changing this up a little bit. I'm going to take this one out. And this one. I'm going to put the load up here. I'm going to take this one out and put a wire here. Then I'm going to take a resistor here. And for now, I'm just going to put the wire here. And this needs to be just 10 ohms. Nope. Still not turning on. Why are we still not turning on? What if I give it a ground? No, that doesn't make a difference. I don't know why that's not working. So there's no reason. What if this resistor's too big? Let's make this resistor 10 ohms and see what happens. No. There's no reason that shouldn't work. I do not. 10 milliamps to turn on. And that's what we have. Holding current. And gate resistance. Well, I am honestly a little... I don't really understand why this is doing this. It's not that. We are feeding it with plenty. There is no reason I shouldn't have. There's no reason that shouldn't work. You know what? Let's see if we can find an example. New blank circuit. Let's go with circuits. Let's see if we can find an example in here. Let's go with transistors, oscillators, Darlington pair. It's kind of it. Schmidt trigger, logic families, active filters, 525 chip. Transmission lines, mismatch lines, low pass filters, miscellaneous devices, tunnel diodes, triodes is... Okay, here we go. Diac, triac, dimmer. Alright, what are they doing? Alright, so a diac is similar to a triac. Okay, so it looks like instead of completing the circuit, they just... So there's a lamp, right? Let me see what they have that set to. 11, 8, and 100, right? So the diac in this case is acting... a diac is similar to a Zener diode, and it basically is... It's a Zener diode that works in both directions. What that means is it's kind of like a pressure relief. When the voltage reaches a certain point, then it allows voltage through. So in this case, if we hit stop, I can explain this. So in this case, that diac triggers as soon as that voltage reaches a certain point. Then the diac triggers, it opens up, and then everything stays open until it reaches 0 again. That's one of the unique things about triacs that makes them a little more difficult to work with, is they won't turn off until there's a 0 potential difference across. So, oh, they did add a capacitor in here. I wonder how much of a difference that makes. I know what that's doing. The capacitor is changing the input of the diac. That is what is allowing... So between this resistor and this capacitor is controlling the on time of the diac, which is feeding... Edit. This is on resistance 500 ohms, off resistance 100 ohms, breakdown. Alright, so I'm going to try manipulating this circuit. And just to see what happens if I just play with this circuit. If I just connect this up to here, what happens? Alright, full flow. What is the difference between this and what I was doing? I genuinely don't know. Yay. Alright, what do they have this set to? 120. Oh! I didn't know you could set that RMS. Alright. Frequency 60 hertz. Okay. What happens if I replace this with another triac? Active components. Triac. And then if I Yep. So in this case, why is that? So this one will turn on if I bypass this. But this one will not turn on. This one won't turn on if I bypass that. Is it because it's before the load? It wouldn't really make much sense, but hell, I'll give it a try. Nope. Is it upside down? I did not see that coming, but all right. Now, the current source, the current throughput of this is vastly different than what it was as if I were to just take this. Can I do a switch? Passive components, active components, unjunction transistor. How about a switch? Apparently a switch is passive. Yeah, that doesn't really seem to make a difference, does it? Nope. Okay. So the problem with my circuit was I had it in the wrong direction. Interesting. MT2, MT1, and gate. What component is this? Oh, that's just our voltage source. Right. Now what if... Alright, I'm going to move this out a bit further. God, this is actually kind of annoying me because... Yeah, this is actually kind of annoying me because I can't draw it in the way that makes sense in my head. I like to lay components out in a way that makes sense in my head, so this isn't really making sense in my head. So what I'm going to do is I'm going to move this over to here. I'm going to put another, I guess I'll put another lamp. No, I'm going to put a resistor. I'm going to put a resistor right here. In fact, I can erase this. I can put a resistor right here. Right? And then I can put another voltage source. So I'm going to take this voltage source away. I'm going to take this lamp away. And draw input sources, AC voltage. Okay, I'm going to make it 120 RMS, because apparently we can do that. 60 hertz. Are you serious? Okay, there is a line and a neutral to the power source as well. Man, we're learning today. Alright, input, voltage source. Oh, shucks. See if I can aim this correctly. No, I got it too low. Dang it! Nope, it's too low. Alright. This is the way that tends to make it easier in my mind. Inputs, 2 terminal. Okay, edit 120 RMS, AC wave, 60 hertz. Okay. Hit. What? Apparently it doesn't matter which direction you draw it in? Ugh. Now, alright. So these are the right direction this time. Edit. 10 ohms. And, okay. Alright, so this time, now that I have this actually sort of functioning, I am going to attempt to... Alright, what if I bring this up here and I come down here like that? Yep, still works. Okay. Now I'm going to put a resistor in here. Right. Yep, that still works. Let me view and scope. Max 168, resistor 10 ohms. So our current should be a few amps. Alright, at this point now, I'm going to remove this noise. And I wish that tail would come out a different direction, but it is what it is. Now I'm going to try feeding this. This is just going to be weird. Now I'm going to try feeding this I'm going to try simulating our opto isolator with input source. This probably won't work right. Now, edit 120. Okay. 120 hertz. And it is doing something, but it doesn't look like it's really... Doesn't really look like it's actually doing much, does it? Properties. Let's slow this scope down. Okay. Yeah, it doesn't actually look like it's doing much. Simulation speed. Edit. 120 hertz. Square wave. Duty cycle. 10. That's still not doing anything. I wonder... Yeah. What can I do? Like, why would you be draining? There's no... It's not simulating this control correctly. I need to come up with something else for this. Yeah, I need to come up with something else for this. Let's try an SCR. An SCR, silicone control, rectifier, active components. Let's try an SCR. Alright, and pull that down, and give this the input I'm looking for. Square wave. Again, how are you? That's... I don't think that's right. All right, you know what? I'm gonna go back to the optocoupler. Building blocks. Optocoupler. That did not place correctly. That works. Okay, now I should be able to give this the input, square wave input, and set it to 5 volts square wave, 120 hertz. Okay, and then give it a ground. Oof. Why? I guess I need a resistor. Ground. All right. Now this is actually doing kind of what I expected, but it is pulsing every time, but it should only be doing half of that. I know why. Now I know why. I need to flip that. Alright, so the reason that this is... What I'm trying to do, again, here's what's tricking this. The triac needs a zero potential. Can you explain what exactly is the reason for doing this? Oh, I did, Rupa, so I did it, I did go through that at the beginning of the live stream. So the whole point of this is we're working on the driver circuit to make our redneck Bunsen boiler working. That's the whole idea to this, is we're trying to design the circuit to make our redneck Bunsen boiler. And part of the problem I'm having right now is that the TRIAC, so a TRIAC, the design of the circuit bridges the two controlled diodes, and because of that, it will stay on as long as there's a potential voltage difference. So if I turn it on and then try to turn it off, it won't work. It'll just stay on. You have to wait to turn it on and then let it turn off when the zero cross happens. So if you look at the pattern here, I can actually show you what I'm trying to explain. This point right here is 0 point. So you'll see my cursor on the screen. So this point right here is 0 point. And what's happening is, and this is the other 0 point, so this would be going up like that. What's happening is right here, we're turning on. This switch right here is turning on at 0. And then it's trying to turn off again at 50%. But because the TRIAC won't turn off until there's zero potential difference, this can try all it want to. This is going to stay on. That's what's happening. So I need to offset this by 90 degrees. I think I need to offset this by 90 degrees. A quarter phase. Let's see what happens. So nope. Still not doing it. Let's try the offset to 120. Yeah, no, it's still not doing it. This is why I need the zero cross detection circuit in there. Because the computer actually needs to count. That's the whole point of this. Yeah, that's the resistor that I'm reading. The whole point of the zero cross circuit in the computer is that it needs to count and not turn this on until it's already halfway through, and then because that's how you have to pulse it. Why? Oh, Jesus. Can I... ...120... 180 degrees is completely the opposite of the 360 degree. Boom! Got it! We got it! Finally! Alright. Now, so what we just did is that by offsetting the phase 360 degrees, we're literally shifting it. Oh man, there's so much geometry that gets involved in this. The sinusoidal pattern, right? We were starting too early, so we're shifting it. So instead of starting on, it's now starting off and then turning on. I guess that's the easiest way to describe it. So by shifting it 360 degrees on this input to this optoisolator. Now, if this were a TRIAC-based optoisolator, we would see the top end of this point as well. But we're not seeing it now because, well, we don't get to. Oh, I kind of want to see the wattage. Show power consumption. That's what I want to do. I kind of want to see that. Okay, 2.8 kilowatts. Not bad. Alright, so now watch this. Now, when I change this duty cycle, it should take it down further. No? Well, I mean a little bit. Let's say make it 2. Let's see what happens when we make it 2. No, we're still... So it's turning on... Yeah, it's still not turning on quite right. I don't think I'm going to be able to emulate the circuit that we need in this program. I might have to search for a different program to emulate the circuit we need. Oh, there we go. Full duty cycle. All right. Yeah, the only thing I could think is if I did another one. So if I took another opto isolator, take this out this way, and this is going to get dirty. I can tell you right now, optocoupler. You know what? I'm realizing just now that I'm using those terms. I'm using those terms backwards. Okay, I want this wire. I want it to go to here. And I want to take and oh boy. I'm going to take this over and I'm going to join it to here. And then I'm going to take this power, come back here, to here, to here, and then a resistor. Wire, ground. I don't, wait, is that? I think I just moved the whole bloody thing into the DC realm. Oh no, it's power. Right, that's power. So now what happens if I take and edit the duty cycle to 50? Hey, I think that worked. Let's change this to voltage and current. Yeah, that actually worked. I can't believe that worked. Look at that. So, this is messy. This is not the way we would do this. So what I've done is I put two transistors. Again, transistors only work in one direction, so current only flows one direction in a transistor. And the opto couplers that this program is using are only transistor-based optocouplers. And so they only work in one direction. So what I've done is I've used one is turning on in the positive pulse, and one is turning on in the negative pulse. And because our input that controls them runs at double the frequency of our line voltage, that causes these to trigger for every pulse of the sinusoidal pattern. So this one triggers positive, this one triggers negative, and it's just a math. So this one does 60 times, this one does a full cycle 60, and this one triggers only every these both trigger twice. Each one triggers one time intermittently every second. It's confusing as hell. I apologize, but that got it to work. I don't know if this doesn't really help me very much. I'm going to be honest. I'm going to have to look for a different simulator. Yeah. I mean, this is the pattern. that we're going for sure. But as far as the simulator goes and the resistances and wattages and stuff that we want to work with, this doesn't really help us very much. What I can do, and we're at the 1 hour mark, so this live stream wasn't very productive, so I'm going to start closing this live stream out now. But what I probably will do is, on the next live stream, we're going to use active voltage to determine the resistance of this element. So we're going to give it voltage, measure the current, and then use Ohm's law to calculate the actual resistance. And then I can plug those resistance values in here, and then I can use that to determine the wattage. Well, I mean, you could use Watt's law to do the wattage too. But putting it in here will allow me to manipulate the resistors to make sure I don't blow anything up. So that's what I'm going to do. So I'm going to call this live stream. I'm going to close it out. I'm not going to save this work because this wasn't terribly productive. Even though we did finally get the Tri-X to work, but yeah. All right. Thank you very much, everybody, for watching. Come back in the next live stream. We'll be far more productive, and maybe we'll try to find a different circuit simulator to do what we actually want it to do. So thank you very much, everybody, for watching. I will see you in the next one. Hopefully you found this entertaining or at least informative. If you're trying to use the simulators too, you definitely learned some things the same way I did. Thank you very much.